R2C meetup, Julia Lawall. Julia is a senior research scientist at Inria and very well known and highly respected in the program analysis and Linux communities and many other communities, like Johan mentioned, like the OCaml community. And Julia actually worked with Johan some years ago on Coccinelle, which was the, should we say, predecessor and inspiration for what is now Semgrep.
Yeah.
And Julia has kindly agreed to share with us some of her learnings, as you can see there on the title, and I'm sure you saw in the invitation. The one note, so we'll record the meeting, we'll make it available later. If you'd like to get notified of future meetups like this one, please join our Slack group. You can go to r2c.dev/Slack, and it'll all work. So with that, thank you very much, Julia, for sharing this work with us today, and I will hand it over to you.
Okay, thank you. Yeah, I mean, I should say in the beginning, the presentation takes up my entire screen. I think you're supposed to ask questions in the chat, but I won't actually see the chat when you ask the questions. And so I will ask for questions every now and then I will go look at the chat and answer them. So, or maybe there's a way for you to make noise. I have no idea. If
I can flag you also if there's a stream of questions coming in. I'll interrupt you.
Okay. So I'd like to present, this was announced, Coccinelle, Prequel, and Spinfer, Automating Summarization Application of Code Evolution's Linux Kernel. So I'm a researcher at Inria in Paris. And this is my work with my colleague Gilles Muller, who's also a researcher at Inria in Paris. And then we have stuck in the middle my PhD student, who is Lucas Serrano, who has worked in particular on Spinfer. And then, as some of you know, this was a project a long time ago. Johan worked on it at the beginning, and I will point out the points where Johan contributed. So basically, the focus of our work is the Linux kernel. The Linux kernel is basically just really, really big. It has lots of contributors, and it has a need for lots of changes. So there are changes that are necessary for security reasons. I'm sure everybody's familiar with Meltdown and Spectre. There's also quite a lot of other security problems. They have to be addressed very quickly. There's needs for change due to performance, new hardware features. Things in general seem to be designed in a bad way, and so they would like to design things in a better way. So with all these people, all these lines of code, maybe this seems like an impossible challenge to keep up with all of this. So fortunately, there's a mitigating factor, which is that in Linux kernel, there's a lot of code which is quite similar to each other. So if I just took some random collection of device drivers here, we can see that many of them, they have little X's where they are using a certain function. Many of them use functions in common. So these functions are organized. Some of the ones near the top are very specific to this kind of driver. The ones near the bottom are very generic to the entire kernel. And you can see, for example, almost everybody's using KZLX. In this driver, everybody's using interface to USB dev. And so basically we have these common functions, these common patterns of code across the different files that we're interested in. And when something happens that affects one of these functions, there's at least a good chance that there's some kind of commonality in how they're used in all of the different files. And so this raises the potential for maybe we can automate some of these changes that we need to do. So we have these opportunities for easing the maintenance burden. Maybe we can script these repetitive changes, and that was the observation that led to the tool Coccinelle. But there's some other opportunities as well. If you need to know how to do a certain change and it relates to some kind of change in the semantics of an API function, then maybe you can look in the history of the software and find other examples of how to do the same thing. If you have some problem, some other people might have had the same problem with this particular function before and need to give you an example of how to make the solution. And so that was the inspiration for the tool Prequel. And then once you have all of these examples, then what are you going to do with them? It would be nice if you could somehow magically learn from all those examples how to perform the changes that need to be done. And that's the tool Spinfer, which is being worked on by my PhD student. So these are the 3 tools that I'm going to present in this talk. So we'll start with Coccinelle. We'll start with the problem of scripting repetitive changes. So basically, the problem that we're addressing is we have libraries. So the Linux kernel has lots of internal libraries. These libraries, they have their interfaces may change. We decide some function needs a new argument. We decide some function should have a different name. Maybe several functions should be merged into one. And when this happens, then we need to update all of the users. And often when you're programming, you think, oh, this decision I made was not very good. I would really, it's getting really tiresome to always call these 3 functions in order like this. Their arguments are kind of tiresome. There's a lot of repetition, stuff like that. I should really do something about this problem and merge these 3 functions into one and get some cleaner, more understandable code. And then you might feel like, okay, but I'm going to have to go and change 500 files. Maybe those functions are not always right next to each other and so on, and it would be really a nuisance. So this is kind of the problem that we want to address. We want to make it automatic to be able to do these things. So here's an example, and so here's a place where Yuan comes in. So this was the first really big patch that we sent to the Linux kernel. Actually, Yuan sent to the Linux kernel. It is taking the kmalloc and memset. So kmalloc is the Linux kernel memory allocation, sort of like the familiar malloc. Memset is a kernel level function, but it's like the familiar memset one. And we take these 2 functions. Often people want to allocate memory and then zero it afterwards. And so there was a special function that was introduced called kzalloc to replace this combination of functions. So it's not really a complicated change, but on the other hand, there have been hundreds of occurrences of these 2 functions. These functions are very common, and so it's a lot of work to go around and update them all. So to see the issue more concretely, we have an example here. We have a call to kmalloc. We have some other code. What this is doing is testing whether the kmalloc failed. If it fails, we want to print something. We want to return something. This part's not very interesting, but then we have a call to memset. It's quite interesting. Memset is memsetting the same thing that we returned from the kmalloc, and the memset is memsetting with 0. And it's also memsetting the same size as we allocated. So we're going to allocate, we want to set the whole structure to 0. And so in the situation where you have this composition of functions, then we want to make this change. And the change will just, you have to look very carefully to see when it's going to happen. Okay, so it's not a big deal. We just changed the M to a Z, just 1 character. It's very small. And we remove the line with the memset. Okay, so you could think to yourself, that's pretty easy. I wouldn't mind, going around 18 million lines of code and making that change. But it's actually not as simple as it would seem. Because it's not all of the calls to kmalloc that have a memset after them. It's not all of the memsets that come right after a kmalloc. Not all the memsets are for 0, and so on. So it's not actually very easy to find exactly which are the places that we need to update. And these occurrences, kmalloc is a function that's used across the entire Linux kernel. You could have to visit 500 different files. It's all kind of a nuisance. And as I say here, there are hundreds of them in the kernel at different times over the years. So that's one issue. So the next thing we're going to look at, that's just kind of a doing something a bit decorative somehow. This code size gets a bit smaller. The code gets a bit more readable, but it's not actually essential to do it. So there's another situation here that I'm going to use as a second example where we actually have a bug. So lots of developers don't understand how to use a particular API, and they all make the same mistake, basically. So we have a iterator, which is called for each child of node. So this is a macro, actually. It's going to do a special kind of iteration. And the very interesting thing is that this iterator hides where it's an issue related to reference count. So it's going to iterate over a list of objects. Each object has a reference count associated with it. And the iterator is going to take care of managing the reference counts. So basically, the bug that happens is that since the iterator is managing the reference count, basically what happens is when you visit one element, you take its reference count and you undo the reference count of the element that was visited before. So then you can go over the entire list and you never have to think about the reference counts. But then a problem becomes if you jump out of the list for some reason. And so if we have a break in the middle of this loop, then we're not going to be visiting the next element. And since we don't visit the next element, nobody's going to undo the reference count of the current element. And so then we will skip the decrement because of the break, and we will end up with a memory leak. So with this particular configuration, with a for each child of node and with the break, there were only 4 occurrences in Linux 4.20, but there's actually a whole bunch of different variants of the same pattern. So you can jump out of a loop with a return, you can jump out of a loop with a goto, and there's a whole bunch of these different iterators. And this is a problem that comes up over and over again because it's like something that's hidden that people have to remember, and people are not so good at remembering hidden things. And so when people add new code, the problem keeps coming back. So basically the kinds of changes that we have seen, they involve scattered code fragments and data flow that have specific data flow and control flow relationships between them. So in the first example, we had the kmalloc and we had the memset. Those are not on the same line. They're not even right next to each other. They can be any particular distance apart from each other in practice. In the case of the for each child of node, we're interested in that iterator. We're interested in the break. We can't just search for all occurrences of for each child of node. There's quite a lot of them. We certainly can't just search for all breaks. There's a lot of those as well. The distance between them is arbitrarily large. And so it's hard to find the place where we need to do all of these changes. Then the second problem is the changes, even if we do find all those places, then we have to go visit them. The changes are widely scattered. And the changes also come in many variants. So you find one, you have to think about how should I deal with this one, find some other, have to think about how you deal with that one, and so on. Okay, so this is what Coccinelle is supposed to help with. So what is Coccinelle? Coccinelle is a pattern-based language for matching and transforming C code. Okay, so or sort of in the beginning, we only worked on C code. We've added some support for C++. And today there's actually a variant for Java, which is kind of a prototype. We've been working on this since 2005. It's been open source since 2008. Basically, the idea is to allow code changes to be expressed using patch-like code patterns, which we call semantic patches, and then be automatically applied across the code base. So we want something that's like familiar to Linux developers. Linux developers are very familiar with patches. This was Yuan's idea. I should note. And we want something that people can write easily, produce easily based on their knowledge of the code. And then on the other hand, something that will be applicable automatically. So we can go back to our starting point as what is a patch? So a patch is basically just like diff. It's a way of describing a change in some code. And in some sense, a patch is a wonderful thing. It's very precise. It's very readable. We can see exactly what's going on here. We can see exactly where this change should be applied, what line numbers are affected, and so on. Normally, you also have the file, but I just cut that off to be simple. It's very understandable what's going on. If you give it to someone else, they can easily understand what the change is, what the idea is. On the other hand, it has some great disadvantages as well. It's very kind of the disadvantages are the same as the advantages. It's very specific to a particular line in a particular file. If you want to take the idea of this patch and apply it to some other file, this description is not going to work at all. This has some specific variable names, some specific constructs that might not be very important. There's some other parts here which are just not important to the change that we're interested in at all, which is the part in the middle here. So there's kind of a mixture of being very specific and being too specific. But the part that we want to capture is the fact that it's readable, that it's code-based, it's easily understandable. So with our semantic patches, what we would like to do is do something like patches, but make them independent of irrelevant details, things like line numbers, spacing, variable names when that's not important, and so on. So basically, we want is something that is derived from the source code, like a patch is, but with a bit more abstraction so that we can apply it across the entire code base. So we'll see how this works with our first example, kmalloc being converted to kzlloc. So to create a semantic patch, you can put yourself in the place of a developer. He has an idea of how he wants to change this particular code. So you can take a small extract of the code that contains the part you're interested in. And then you can kind of think about it and say, okay, some parts of this are important. So kmalloc is important to the change that we want to do. memset is important to the change that we want to do. And 0 is important to the change that we want to do. And some other parts are not so important at all. So this whole if not fh stuff, it's kind of important to the semantics of kmalloc, but it's not important to our specific change. So what we do with that to get started is we just get rid of it. So that's the first thing we do. Okay, so I didn't completely just get rid of it. I took it, we had this code, and then I've replaced it by ... So ... has a very specific meaning in the case of Coccinelle, but it's ... is also designed to be sort of intuitive to the developer. If you were going to describe this change to a colleague, if you were, for example, writing this on a napkin at lunch or something like that, you would probably say, okay, we have a kmalloc and then ... and then we have memset. So it's designed to be intuitive in that way. So now we can keep going. The next thing we're going to do is we're going to take this code, this original code, and describe the change that we want to make. So basically, we're going to follow the patch idea. In a patch, there's some lines you want to remove, some lines you want to add, and there's some other lines which you should match and are not going to be removed and added. But basically, the removed lines, you put a little minus in front of them. The added lines, you put a little plus in front of them. And everything is simple and straightforward. So that's what we're going to do next. Basically, what we want to do is we want to remove the kmalloc line, and then we want to add something that looks almost exactly like it, but we've turned the M into a Z. And the memset line, we just want to remove. So this is our transformation. On the other hand, this is still too specific to the particular code that we started out with. So we need to do the abstraction part. So the next step is going to be to take the parts of this which are not important to our specific change and convert them into what we call meta variables. So there can be variables of the pattern matching process that are going to match different terms in the code. So that's what we've done here. We declare our meta variables. We say this should be an expression. You can say this should be an identifier, this should be a statement, and so on. And then we use our meta variables at the appropriate places in the matching process. So in general, for example, we don't care about the arguments, so we just put E1, E2. We don't care about the return value, so we just put X. On the other hand, we're going to use those arguments when we construct the plus code. We're going to use the arguments also because we want to be sure that the return value of kmalloc is going to be the first argument to memset. But now we have a complete semantic patch, and we can take this using Coccinelle. It's a command line tool. You basically make a file with this specification, and you run spatch on this file and on the directory, the path to your code base, and it will go around and make all the changes for you. So do you have any questions at this point? Questions?
I don't see any questions in the chat, but people can speak up. If not, I have one question.
Yes.
These changes you talked about, the how many times these functions appear across the code base. How do you think about testing these changes? How do you approach testing it?
So that's not our problem. So our problem is to help you make the changes, and the people should test the changes in whatever way they test the changes normally.
So it's part of the kind of Linux code management, change management system.
Yeah, they will have unit tests or test suite, and also the compiler. If you make a change that is not valid, also the compiler is the first line of defense, and then there's test after that. So
yeah.
But yeah, that's not the goal of the tool. It will change the semantic, so that's the goal of the tool.
So actually a detail that I didn't include was that we're not actually changing the source code by default. The default behavior is to produce a patch, and then you can study the patch and you can apply the patch to the source code if you like it.
Got it. Thank you.
So really, we're trying to help you do what you would otherwise have to do by hand. We're not trying to provide a magic tool that will take you from old code to perfectly working new code. We're providing you with a programming language for specifying changes, and as with any programming language, you can do good or bad things with it as you like.
Thanks.
Okay. So any other questions? Any objections to what I've done so far?
Isaac had a question on the ... and the control flow graph. So I guess perfect transition for you.
Yes. So what was Isaac's question? So should I find it or?
I can
read it, or Johan can. I was just asking if there's any awareness of the control flow graph with the ... operator.
I see. Okay. Yes. So there is, that's what the ... operator means, actually. So when you're looking at this specification, you might think it means that kmalloc is on line 3 and memset is on line 5, and kmalloc is before memset. So that's not actually what's going on inside. Actually, we have a control flow graph. The ... is following the control flow graph. And the ... by default here is going to check that on all of the paths in the control flow graph, we have a memset that satisfies the pattern. So we do that kind of sanity check that you have really understood how to describe the code that you're working on and the change that you want to do. If you don't want the for all behavior, you can also specify exists, and then it will check that there exists a control flow path from the kmalloc to the memset. So any more issues?
What does the syntax look like for the not for all case, like the partial path?
You can
Maybe
put when
later.
exists here next to the ... If you say when exists, then it will switch it to just there exists a path from one to the other. You can also specify that your entire rule should be exists by putting exists at the @ sign at the top. Okay. So there's another thing that you could be concerned about, which is here we have X and here we have another X. And actually, the only thing these two occurrences of X mean is that we actually have the same code in the two places. There's no guarantee here that the X is actually the same thing, or that the X actually has the same contents. This memset thing, it's a bit tricky because memset, the goal is to zero something. And sometimes you want to zero something just because you want to initialize it in the beginning. You've just initialized your structure, and then you want to put zeros everywhere. And in that case, kzalloc is relevant. In other cases, you put zeros everywhere because you put some stuff in that buffer, and you don't want this code that comes afterwards to see that stuff. And so I haven't done anything here to ensure that I'm in the first case and not in the second case. To put it another way, the kmalloc and the memset might be 3 lines apart, like we saw in the original code, or they might be 1,000 lines apart at the moment. It could be like a memset at the very end of the function. So we need to sometimes be a little bit more specific. So basically the idea of Coccinelle is that we want to stay very close to the C code. So we've already added one operator, which is ... But we don't want to add some kind of strange language things that people have to learn about and think about and so on. But here we had to make some kind of compromise because we need some way to specify what's allowed in this ... region. So we have this when thing, and this is saying when there is no, for example, when there's no function call on X in between the kmalloc and the memset. So the idea of a function call is the only reason to pass to another function an unallocated, uninitialized fragment of memory is to initialize it. The other thing that we disallow is an assignment, and this is some kind of strange notation. What this means here is that X is a sub-expression of the left-hand side of the assignment. So it's going to forbid X equals something. It's going to forbid x arrow y equals something, it's going to forbid x arrow y dot z dot whatever. Any kind of complicated thing is like if x is on the left-hand side. And with this, we can be more confident that our thing is correct. We can't be perfectly confident. There could be some other ways, strange ways, in which, for reasons for which we need the mem set here. But this is kind of the idea of how we think that people should use Coccinelle, which is that you express what you want to express, you make it as safe as you want to make it, and then you can test it. And if you find that it's not safe enough, then you can go back, and since the specification is very simple to understand, then you can refine it if you need to do that. So in our particular case, in a very recent version of Linux kernel, it updated 14 occurrences. 5 of them are false positives. That is, the mem set was actually important for something. We shouldn't be merging it in with a kmalloc. We could have added more when tests, but again, with the methodology I was saying, at some point, we can also just decide, okay, we don't want the perfect semantic patch. We make our semantic patch as well as we need it to do the change that we want, and once we're satisfied, then we can move on. But then the more interesting thing is that, okay, kmalloc and memset, it's quite well known at this point in the Linux kernel. It's been actually there for, this issue has been around for like 15 years at this point. But there's also a whole bunch of other functions in the Linux kernel which also have this zeroing property, and that people might not want to know, might not know as well as they know the kmalloc and memset issue. And so once you have the rule that I wrote on the previous slide, then it's very easy because everything looks like code, everything's text-based, to make other variants for all of these other kinds of functions. And then we can get lots of rules that will do things that are somehow a bit more obscure that you could also communicate to other people, and then they can learn more about how they should be developing the Linux kernel. So I have another example. This is the one we saw before with the bug. I'll just go through this very briefly. This is the semantic patch for finding and fixing the reference counting bug. So we have our for each child of node. This is, for each child of node is a macro, and it is being used as a loop. And so we have to declare that declare that situation somehow. So basically this macro, the second argument is the one that has the reference count on it. And what we want to do here is, if we go through the control flow paths through the loop, if we find a break, so the question mark is if we find a break, and if along this control flow path before the break there is no of node put, that's the function that decrements the reference count, or there's no assignment of this reference counted thing, which would require keeping the reference count higher, then we want to put a of node put in front of the break. And actually in the break case, there's another consideration. We also want to be sure that there is no the reference counted thing after the loop as well. So again, this is quite a simple specification. It's a bit more complex than the previous one. We can take this and we can apply it over our kernel. We can apply it perhaps every week over our kernel, since I said that this is a recurring problem. We can find the problem, we can fix the problem, we can submit the patch, and so on. So, so this is the number of this kind of issue. We had 4, as I mentioned, 4 with a break, but then there's quite a lot with a return as the way of jumping out of a loop, with a goto as a way of jumping out of a loop. And as we saw also in the previous case, there's a whole bunch of these looping, iterating things, all of these managed reference counts, and we can see that there's been lots of problems with all of them. And even, I mean, it's kind of as a side benefit, once you have found these problems and once you've gone and looked at them, then you can even actually find other reference count problems, and we can write semantic patches for those other reference count problems. So in general, whenever you do things I mean, it's kind of in a very large code base, if you have 18 million lines of code, anything that can go wrong will go wrong somewhere. And being kind of oriented to the places that are problematic can be helpful to find these different kinds of bugs. Are there any more questions now?
No, I was just curious how many rules there were right now in the Linux kernel. How many semantic patch and rules there were right now applied in the Linux kernel?
applied, so there's like 8,000 patches that mention Coccinelle in the Linux kernel. There are about 60 semantic patches which are part of the Linux kernel distribution. Okay. I think there is also much more use. Sometimes there's some people who use Coccinelle in the Linux kernel. You can kind of see from the changes they're making and so on, and then they don't remember to mention Coccinelle in the log message, so there's no proof that they used it. But I think the use must be even higher than that. Okay, so now I'll talk a little bit about how it works. Basically, we have the semantic patch world and we have the C code world. A C code, it's a file. It consists of a sequence of functions. Those functions, as we've discussed a little bit already, they get converted to a control flow graph. The semantic patch, it gets converted to CTL. CTL is computational tree logic. This is a form of temporal logic. The idea is it allows you to reason about paths. So this is what we need for our ... operator. It's like if from our kmalloc, there are paths that are going to, in the control flow graph, that are going to connect us to memsets. So once we have our formulas and we have our graphs, then we're going to use a form of model checking to take the formula and find out where it matches in the graph. If it matches somewhere, then we can collect information about the metavariables that are present in the semantic patch, and then we can use that in order to figure out how to make the transformation. And then this is just an iterative process. We take the first semantic patch rule, we apply it to all the functions in the file, and then we move on to the next semantic patch rule. And so the next rule can see the changes that were done by the previous one. On the other hand, there's no iteration. We never go back, and so we're guaranteed to terminate. So I'll talk briefly about processing the C code and then processing the semantic patch. So our goal is to process real Linux source code. We want to handle as much as possible the entire C language. So this is something that Johan was very helpful with. He was the one who worked on the C parser. We have a dedicated C parser. It keeps space and comment information. It's going to, and we're doing source-to-source transformation, and so that's going to let us produce code coming out the other side that looks exactly like the code that we got in the first place, except for the change that we want to make. So we want to integrate into the Linux kernel development process. People are going to have to be maintaining the code that we produce afterwards. So it has to look the way it was in the beginning. Another interesting thing is that we do no pre-processing whatsoever. That is, we don't expand macros, we don't interpret if-defs, we don't run the C preprocessor in general. This has lots of advantages. One of them is that the code that the person is going to work on is internally, it's exactly like the code that he sees. If he sees a macro call on his screen, he can write a rule in terms of that macro call. Another advantage is that if we're not expanding those macros, we don't know how, you have to know how they're defined. And so we don't actually have to even go and find and parse and think about most of the header files. The Linux kernel, the code base is very big, but every file is going to include lots and lots of header files. And so in the cases where we don't need the header files, this is a huge performance improvement. And we only work at one function at a time. Our intuition here is that basically when you make a function call, you might go to a lower level of abstraction. And in general, the kinds of changes we're interested in are kind of all at the same level of abstraction. We're interested in kmalloc and memset. We're not interested in how kmalloc is actually implemented. There is a way that's kind of working by hand somehow to do something interprocedural, but it's not very convenient somehow. So this is a little bit of a limitation for certain kinds of rules, but in many cases it works quite well. And again, it's also great performance improvement because often when you search through function calls, those function calls are not going to get you really to the place where you want to go. So for the processing of the semantic patches, our goal for the semantic patch language, basically you should be thinking about the semantic patch language as it's just like C. Or maybe it's just like C with some ... and some metavariables. But actually it's those things, but it's also going to let you talk about just expressions or just types or just field names or something like that. You should be able to express changes at all different levels of the code, of the syntax of the language. The rules should also be concise and readable. So to provide all of these things, we actually have a separate parser for the semantic patches. We support most of C, and as I mentioned, we have a few extra extensions. One feature of the Coccinelle is that it's very close to the C code. In general, that's a good thing. It lets the developer reason about the code in terms of what he's familiar with, but sometimes it's too low level. So in C, you can say x equals null, or you can say exclamation point x. Those are both going to do null tests if x is a pointer. And you don't really want to have to write both of those every single time you have the code want to match code that's doing a null test. So there's some rewrite rules that are applied to the semantic patch that make it more general in these kind of very generic ways. And as I mentioned before, it's implemented by a translation to CTL, and this allows both for all and exist quantification over paths, and you can mix them in a single rule. That's probably something that very few normal users actually ever do, but the possibility is there. So here's the 8,000 patches. You can see in the beginning, we started out a bit slowly. So this is most of our effort, maybe Johan's effort as well. In recent years, we have had kind of other things to do. And so these are more what Linux kernel developers have done. And so you see many years, I mean, it goes up and down, but in many recent years, there have been more than 1,000 patches that are developed using Coccinelle in some way.
Cool.
So Coccinelle, it helps the developer express his knowledge about how changes should be done. It's good for communication. People can read it. Sometimes you make a patch with Coccinelle. You might say it was done using Coccinelle. Your semantic patch might be a bit large. You might not feel like putting in a log message, but sometimes people ask for it, and it's because it makes a documentation about what the person was thinking about, what were the considerations he took into account. Other people can look at that very concise specification and realize that some cases were missed and there might be some problems, and so on. In general, Coccinelle is a way of matching C code, and so you can use it for counting the number of switches in your code base versus the number of ifs, for example, if that's something you're interested in. You can also use it for finding bugs. So the example that I showed, we found the bug and we fixed it, but sometimes when you have a bug, the bug format is very typical, but the fixes are going to be very specific. And so it's also useful for just the finding part. As I mentioned previously, we support some C++, and we have a variant for Java. And at this point, I think it's pretty well adopted, well understood. People are familiar with it in the Linux kernel development.
Actually, I was surprised because we announced a few times like Semgrep, our version of Coccinelle in some sense.
Mm-hmm.
On blog post and on Twitter and many times. I was surprised, like, but this is the same thing that Coccinelle.
I see. Yeah.
So people are quite familiar indeed.
Yeah. So it's the tool is open source, and when you're open source, you have no idea actually who's using what you do. So
yeah.
And people also don't often the people we know about are the ones who complain, and when they complain, they don't always say exactly what they're doing. So I don't really know, in all of the communities that might be using it. But there's some negative aspects. Coccinelle, you have to know what you're doing. You have to enumerate somehow all of the changes you should make. And so if it doesn't help you if you don't know what to do. I mean, if you have no idea what to do, it's going to be hard to help you. But if you have some partial idea what to do, that's a situation one might want to consider. And it also...
Sorry, Julia. Yeah, usually I just one question. He wanted to know how much effort it will be to port Coccinelle to another language, like to do transformation for Go or for Rust or...
Yeah, so usually my answer is it would be a lot of work. Coccinelle, internally, it's kind of like a compiler. So we have maybe 20 passes, and every pass is a big switch over the abstract syntax tree. And so other languages might have a different abstract syntax tree. On the other hand, the person who did Java, he did it it was like a future PhD student who did it in about 3 months or something like that. So if someone, Coccinelle is written obviously in OCaml. And so if someone is a good OCaml programmer already and kind of a courageous person and everything like that, maybe it's possible to translate it to Go or some kind of other imperative language in a moderate amount of time. Other questions? Okay. And it doesn't help to understand what others have done. So we have all these recurring changes. How can we actually looking through hundreds of lines of patch code is kind of tiresome. So this is another issue that we have to address in kind of the maintenance at a large scale. So I will talk about these other tools kind of much more briefly because time is moving on. The second tool is targeting the problem of finding repetitive changes. So basically, we're still in this situation. We have our library. It has changed in some way. And maybe some function has more arguments and stuff like that. So what should we do in order to change all of the users of this function? How can we find examples that are going to help us make the change? So for example, you submit a patch to Linux kernel, somebody tells you, okay, your patch is okay, but we don't like kmalloc followed by memset anymore. You should be using kzalloc to be kind of up to date with the modern Linux kernel coding style. And so then, the developer doesn't want to look ignorant, like he never heard of kzalloc before. So he has to go off and try to figure out how should he do this. Okay, so somebody told him he has some information. We have a call to kmalloc, we have a call to memset. Kmalloc is followed by memset, but that's kind of all he knows. So to address this problem, we've developed the tool Prequel. And with Prequel, we have an analogy. We make the analogy between performing code changes and matching changes. When we perform changes, like with a semantic patch, we need to describe the changes to match and remove, and we need to describe the code to add. And we want to match changes. We also need to describe things. We need to describe the code that should be removed, and we need to describe the code that should be added. So there's a lot of describe and code in these descriptions that I've made. And so what we want to do is kind of repurpose the semantic patch language to make a query language for patches in a Git history. So basically, in our situation, we know, as I said, we know kmalloc comes before memset, and it's supposed to become kzalloc. So I guess here I actually kind of cheated because I guessed that kzalloc was going to be replacing the kmalloc instead of matching the memset. So you might not know that, or you might not. But basically, you can just make a description that contains the part that you know about. You can use meta variables as well, but I've just put myself in a situation where I'm pretending I don't know what the meta variables involved are. And so now we have a patch query. This patch query, the important part about it is it's going to actually have this control flow property, this remembering that we need the kmalloc and the memset to be connected to each other. So we can take this patch query and then we can run it with Prequel on some versions of the Linux kernel. So I took 3.0 to 3.5 because this is kind of an old change, and so I took some kind of old versions. And Prequel generates a list that looks like this. And so this list is a list of commit IDs in the Linux kernel. And then we have some percentages here, and these percentages are telling us the degree to which these patches matched the thing that we were looking for. And then there's some numbers here which are not terribly important. But the point that I want to make is that another way you could do this kind of search is you could just go for git log, and then you could use /, you could just search for kmalloc. But that will give you the most recent change about kmalloc. And the most recent change about kmalloc is not necessarily the one that you're most interested in. Probably actually for a simple thing like this, maybe the older changes are the ones you're most interested in. So this is the ones that are giving you the 100% match or the pretty close match Or maybe this patch down here, 7F967, maybe that's one we would just not want to pay attention to at all because it seems like a lot of other changes are happening. So Prequel gives us some examples of how to make a change. It can also be useful for metrics. So if you make a fancy new program analysis that is searching for a certain kind of thing, you can also use Prequel to find how many people have fixed that other thing before and to see how useful your new analysis is going to be. Prequel is actually very closely tied to Coccinelle, and so it supports all the same things that Coccinelle does, including Java. On the other hand, the weakness of Prequel is Prequel will find a bunch of patches for you, but human intervention is still required to actually figure out what those patches do. So that brings us to the last tool, which is Spinfer, where we have all our examples that we found from Prequel, maybe we got in some other way. And we want to figure out what those examples are actually doing, and then ideally to apply those changes that are made by those examples to our new code fully automatically. So now we have actually the whole loop. If we can make this Spinfer thing work, we can describe our very approximate knowledge with Prequel, and then we can get examples, we can generalize those examples, and then we can apply those examples, and we get our modernized code base. So we have the same problem as before. Don't use kmalloc followed by memset. Use kzalloc instead. So basically, Spinfer, it's going to take our patch examples and infer a semantic patch that generalizes the changes. So this is a really hard problem. The other tools that I talked about, maybe it seems like they do something useful, but there's the human in the loop. The human has the idea of what he wants to do, and then his problem is just to describe in a formal way what should be done. Here, we have a bunch of information, but we're not relying on any human intuition. The tool is going to have to figure out everything that the human would be figuring out in the other situations. So the human has to figure out the boundaries between different changes. The human has to figure out where there should be control flow constraints, how the very information should be propagated in different places using meta variables. There could be many different variants of the change. We saw that in the case of for each child of node, sometimes we have break, sometimes we have return, sometimes we have goto. And we also have to recognize noise. There could be some changes in the collection of patches that we have that are actually not relevant to the thing that we want to do. So, as I mentioned, this is what my PhD student has been doing. So basically, it's like a really complex search problem. He's broken it down into 3 phases. First, we find the common parts. So for example, in our kmalloc memset examples, we could find a bunch of calls to kmalloc in our different patches. We could find a bunch of calls to memset in our different patches. Then we try to generalize those clusters of common code fragments. These are going to give us things that are kind of like lines that we might put in our semantic patch. And then we need to connect those pieces in the semantic patch according to the control flow constraints in the original code and according to what we call data flow. It's not really data flow, but it's like matching propagation of different pieces via meta variables from one part of the rule to another. And so these are addressed one by one. In particular, the collection of the common fragments doesn't take into account the control flow. It's kind of a correction that happens in the end. So all I'm going to show is some results. So this is what Spinfer does based on one of the patches that was found using Prequel. I picked a patch that has about 10 examples in it, and so we have some variety we can actually learn from. So on this example, Spinfer generates 3 semantic patch rules. What I'm showing here is the second one first. The second one is the one that's the most like what we saw before. We have our call to kmalloc. We have our call to memset. These are getting removed, and the call to kzalloc is getting added. So you can see Spinfer provides you some other information. It tells you what files and functions this transformation was inferred from. And it also tells you if there are some false positives that are generated by this rule. So if we look at this rule, maybe it's a little bit different than the one we saw before. It's got this GFP kernel thing here. We didn't have that in our previous rule. That was just a meta variable. It doesn't have the when stuff that I added. Actually, limitation of Spinfer, it's only inferring positive things. It doesn't infer negative things. This GFP kernel thing, it's not something that's actually required for this change, but Spinfer can only learn from the examples that are offered to it. And all of the examples have GFP kernels, so Spinfer, its only thing it can do is to assume that GFP kernel is important. So there's some aspects of this rule that are maybe not quite perfect. The user could leave them as they are and just use this rule and have a more specific case that is necessary, or the user could actually look at this text-based representation and generalize it some way if he thought it was important. There's one more difference, which is here we have size of star E0. In the rule I wrote by hand, I required that the expression, which is the first argument to kmalloc, be the same as the expression, which is the last argument to memset. So by using Spinfer on our examples, what we have learned, we've actually learned something. We've learned that there's actually another variant that we have to take into account. So this is kind of the summarization benefit of Spinfer. You might not notice it. I mean, this is all that it says in the log message. There's nothing particularly interesting about that. And in glancing over the patch, you might not actually notice this particular issue. So this is a pretty much of a success for Spinfer. Now we can look at the other two rules, which are perhaps a bit less successful. This is one where we have this situation of finding the boundaries between different rules. So Spinfer has actually makes an effort to do that, but hasn't completely succeeded in this case. So here we have several kmallocs in memsets. The first one here where it's turning into kzalloc. Here's another one where it's turning into kcalloc. This is something with 3 arguments, and it's used for big arrays. And ideally, we would like that these should be 2 separate rules. Well, however, I think the reason why it came out this way with them stuck together is because there are not very many examples with kcalloc in our particular patch, and so it wasn't motivated to make a specific kcalloc rule. And then there's another strange kcalloc at the bottom line, and this is actually kind of a failure of Spinfer. I think it thought this kcalloc on the bottom line actually has the usual kmalloc and memset that are associated with it, but for some reason it seems that Spinfer has thought that they are noise and discarded those. So this one, you can see it's only inferred from one example. It's kind of a strange thing, but still we do learn something from it. We learn about the necessity to take into account kcalloc, and since we have a textual representation, the developer can also edit this textual representation in order to get a rule that's specific for this thing that's highlighted by this particular example. And then the last example, again, it's more specific as well. This is a case in the source code where the developer, instead of doing the typical thing where they have you kmalloc, you have your failure test, and you have your memset after the failure test. Here we have an if, which is testing for the success case. And then it has a if and then and else. It's a bit complicated. Then this time is the success case and the else is the failure case. And so the change is in a different way. Again, we learn something from the change, which is that this different kind of if and this different kind of placement of the success code is possible, and it's something we might also want to think about. So overall, on this problem, Spinfer produces a semantic patch that contains 3 rules. It has a precision of 86%, meaning that 86% of the lines of code that it changes, it makes the correct change. It has a recall of 89%. It makes 89% of the changes that should have been made. And 5 out of 7 functions that are affected by this patch were changed completely correctly. This is a more general experiment. We took 40 widespread changes from 2018, and we saw to what extent Spinfer was able to reproduce them. On the left-hand side, we have the synthesis example, which is where we take the entire set of patches for this particular change, and we see what is the ability of Spinfer to summarize those patches accurately. On the right-hand side, we have the transformation experiment. Here we take the first 10 files that were changed, we try to infer a rule from it, and then we try to apply that rule to the rest of the changes. There's also the left side and right side of this example. There's some features, Spinfer is not actually perfect yet. There's some features of changes that it addresses and some that it does not. In particular, we already saw that it doesn't infer negative constraints on ... It also doesn't infer constraints about interprocedural analysis and so on. So it does pretty well on the left, the part in the darker color, which is what we target. It does a bit less well on the things that we don't target. That's not surprising. But still, it can produce something in most cases. And then this can be something that the developer can afterwards modify by hand. Actually, once he's been reminded of what the syntax of Coccinelle is, then it might be easier for him to figure out what's the proper semantic patch to make. Again, a transformation has pretty high precision. In some cases, it has lower recall because, as I mentioned in the previous example, it can only infer things based on the information that it's given. And the first 10 changes, first 10 files containing changes for a particular change don't necessarily illustrate all of the possible changes. So in conclusion, basically what we're proposing is a pipeline for automating, summarizing, and performing evolutions. First, we can have Prequel to find the examples, Spinfer to infer semantic patches from the examples, and Coccinelle to apply the results to the code. And a nice feature of this is every tool has the input and output as source code. This is something that you can modify. You can modify the specification. You can offer it to someone else. You can understand everything that's going on. And so even if the result is not perfect, it might be perfect in some cases, but it might not. You can always refine what you're doing, improve, and get everything to be more automatic. So as I said, semantic patches represent an intermediate step that is useful in all of these different processes and that allow user customization and communication. So things that we're interested in doing with this, if we want to backport things to older kernel releases, then there will be a whole selection of API changes. We need to find out how the changes have to happen. We need to find out how we can do the updating. And then you can, for example, backport very modern device drivers to the old kernel that you have on the machine that you don't want to change, and so on. Also backporting specific patches. If there's a bug and you're running an older kernel and you want to have the security fix for your kernel, and you can, or our goal is that you can use our tools to backport the patch to the older version. We can also go in the opposite direction. If you have out-of-tree code and you want to integrate it into the Linux kernel, it's going to have to integrate with the latest version of the APIs. And so again, you may need to make these kinds of changes. And another use case for this entire pipeline is to make Coccinelle more accessible to new users or to infrequent users by giving them some idea of how a semantic patch would look like for their particular problem. So all of these tools are open source and all of them are available at different places. Coccinelle is definitely the most mature of these tools. You can also find it in GitHub. But the others are available and we use them all the time ourselves, and so hopefully they should be reasonably usable by other people. So that's all I have. Do you have more questions?
Woohoo! Thank you.
Thank you, Julia.
Thank you.
Thank you.
Thank you.
Let's see if there are any more questions.
Yulzi had a question on a technical question, I think, on the slide 21 about the more complex semantic patch.
Okay.
I don't know if Yulzi is still here, but I think there was a when not equal. I think he wanted to know how does it work, the when not equal, e equal child. Yulzi, are you here still?
Yeah, I'm here. Yeah, thanks for the talk, Julia. It's really great to see the predecessor of SCREP. What I was kind of confused about with the when statement was like, so you have expression declared at the top, but then you're doing an evaluation to see if E equal to child, and what is this child? Like, is this a string literal you're matching, or is this an expression that you're matching?
So child, it says at the top, it says it's a local ID expression, so it's a local variable. And child we'll figure out what child is when we come to this for each child of node, because it's kind of unambiguous here. It has to be the second argument of the for each child of node. And then now that we've decided that child is going to be X or A, or well, it has a local ID, so it's just going to be some variable X maybe, then that's going to be fixed for the rest of the match of the wool. We are, yeah, so we know what child is. Now we come in here, we look for, we check that there are no of node puts of whatever that child thing was, X or Y or whatever it got bound to. But then it's reasonable to ask about this E thing here. What is E? Where did we decide what E is going to be? So actually in the semantic patch, all these variables are quantified. And they are quantified as tightly as possible. So basically, like for child, the quantifier is at the top, and so all of the occurrences of child that are matched are going to have to be the same thing. But this E, the quantifier is just tightly wrapped around the E equals child. So this is just an assignment. It's a pattern which is matching an assignment. And it's like for all E, E equals child. So it's like basically this is saying there should be no assignment that has the any left-hand side at all, and a right-hand side, which is the child that we matched in the first line.
Okay, I think that clarifies it. Okay. I had another question. If you're taking more questions, I don't know how we're doing in time.
Yeah.
So I was curious about the Spinfer. So you said it's an inference engine, but like under the hood, like, is it using some kind of inference algorithm? Like, what is the actual inference logic that is implemented?
So basically what happens is here, so first we have clustering. So it is using some hierarchical clustering algorithm. And this clustering is done without any idea of how these clustered things are going to be used. So we take basically all the calls to kmalloc, those are going to get clustered together because they're kind of similar to each other. I mean, that's just my intuition. The algorithm obviously does whatever it wants. And probably all the memset calls will be clustered together because they're kind of similar to each other. Then we have a bunch of clusters, and we try to take those clusters and we try to move them together to form a semantic. We try to connect them to each other so that they form a semantic patch rule. So we can take our kmalloc cluster and we can take our memset cluster, and then we look at every instance, every piece of code in the kmalloc cluster, and we see that it's connected by a control flow path to some instance in the memset cluster. And when that happens, then we can actually connect them together. On the other hand, it might happen that
you connect them with a ...
Yes, with a ... Thank you. But it might happen that in some other rule, like we have some kmallocs, and some of them are connected to memset, but some of them are connected to some other thing. So we have started our rule with all of those kmallocs together in one cluster, but we're not going to be able to extend it because some of them have memsets afterwards and some of them have other things. And so then we dynamically split our clusters so that we can keep together all the kmallocs that go with memset, and then later on in the future, we will work on the kmallocs that go with some other thing. So that's the second phase. And then the third phase is worrying about the meta variables. So kmalloc, it has 2 arguments. Memset has 3 arguments. You can imagine that could be some kind of mixing of the way the variables are, I mean, not in this particular example, but sometimes maybe the first argument of kmalloc goes to the first argument of memset, and sometimes maybe the first argument of kmalloc goes to the third argument of memset. So in that case, it might not be, everything might work out for the control flow, but there might not be any consistent way to assign the metavariables. And so again, we split things. And so you can see that splitting in the example I have here. Here we have like E0 equals kmalloc E1 GFP kernel. There's actually a cluster which is being represented by this thing. And this particular thing here, it reappears, it doesn't reappear in this one's quite different. But here we have exactly the same thing again, E0 equals kmalloc E1 GFP kernel. And so there was a cluster, and then we found that in one case, in most cases, we just have the direct ... to memset. And in some cases, we have some other strange control flow. And so then we had to split. But when we did the splitting to keep things generic, we kept this E0 equals, that was something generic that was based on the entire kmalloc cluster, as opposed to just a little part that we split off. Because otherwise the split off rules would be completely specific and wouldn't have any chance to match anything else. So the approach, it's pretty, I would say it's kind of very directed. It's not like there's no kind of, except for the clustering, there's no like machine learning magic here or anything like that. We're following the control flow relationships that we find. We're following the data flow relationships that we find, and we try to bring things together in a good way.
All right, thank you.
But you actually, the paper got accepted? Or
yes, so, I mean, it's like shepherding. All papers are shepherded, so.
Okay, so there's a paper at Usenix, I think this year, about Spinfer.
Yeah.
So,
Nice. Congrats.
Yeah, very nice. Yeah.
Thank you.
All right. Thank you very much, Julia.
Thank you.
I don't know if we have other questions or...
One came from Drew.
Yeah, Drew. Yeah, Drew has a question.
Hi, Julia. Thanks so much for the talk. I was curious if you had tried to apply the same patterns at some like Clang IR level or other kind of compiler intermediate language, or if that even makes sense. We're just trying to think about ways like to go back and answer the question of how you could apply this to different languages.
So I'm not completely sure to understand the question. Because so if is your idea, what if we made a Coccinelle for Clang IR? Would that be a good thing to do or not? Is that the idea?
Yes. Mm-hmm. Correct.
Okay. So I guess it would depend on, yeah, I'm not that familiar with Clang IR, so I'm going to pretend you said assembly language. So it kind of depends on what you want to do. If you want to find bugs, for example, if you want to find double locks or missing locks, something like that, then you're just interested in the control flow, and it's just like function calls in control flow. And so it doesn't really matter whether you actually, this close connection to between the pattern that you're writing and the code on which it's going to actually be applied, it doesn't really matter. On other things, though, if you want to reason about variables or dereferences or other kind of low, kind of syntactic kind of things, I'm not sure that working at the IR level would be very convenient for the user.
But for Drew, for the program transformation context that is Coccinelle, because Coccinelle is to do source-to-source transformation. It's not for finding bugs. And so
yeah, so that's obviously sure. That's obviously the other issue is that the Linux kernel developers will not be very happy when you transform their nice C code driver into a IR driver.
Yeah, once you're into the Clang IR, there's no way to go back. It may be an advantage to go down really, but then you cannot go back. So you're
great. Thank you.
I don't know if we have questions from external people. Don't be shy.
A lot. I had a couple during the talk, but they ended up being asked by other people first. So.
Okay, cool.
But thank you very much. This was super
Okay.
informative. I just love Coccinelle. Like, it's such awesome software.
Okay, thank you. If anyone wants to use the tools, we have the URL on the last page, and you're welcome to contact me. We have a mailing list for Coccinelle. We are happy for questions. We try to answer them in a reasonable amount of time. So
this usually means the day after, by the way. Okay, good.
Thank you so much, Julia.
Yeah.
Okay, thank you very much.
Yeah, that was great. Thank you so much.
Okay.
Thanks everyone for coming.
Julia.
Yes, thank you.
That's great.
We'll try to.
Thank you so much.
We'll try to steal more ideas and make money out of it. Ciao.
Okay. Bye-bye.